The first message I saw was not from monitoring. It was from support. Users saying the site is unsafe, browsers blocking checkout. Seconds later, PagerDuty fired. TLS handshake failures above threshold. Then Slack. Chrome showing certificate warning. Mobile app cannot connect. Seeing spike in connection resets. I opened Grafana. Request rate was dropping, not gradually, sharp decline. At the same time, handshake failures were spiking past 60%. CPU looked fine. Pods were healthy. Ingress was up. But traffic was being rejected before it even reached us. That was the part that made it worse. Users were not seeing our errors. They were being stopped by their browsers. We were running on AWS, EKS cluster in EU West 1 with a secondary cluster in US East 1. Traffic came through CloudFront, then hit an application load balancer. From the ALB, traffic flowed into our NGINX ingress controller inside Kubernetes. We served a web app and a set of APIs, roughly 3K requests per second at peak. TLS termination was handled at the ingress layer. Certificates were managed using Cert Manager with Let's Encrypt. We used HTTP 01 challenges routed through the ingress. Certificates were stored as Kubernetes secrets and automatically renewed. CI/CD was GitHub Actions building images and Argo CD syncing manifests. Everything was automated. At least that was the idea. Monitoring stack was Prometheus, Grafana, and Loki. We also had synthetic probes from multiple regions checking HTTPS endpoints every minute. Users reported seeing connection not secure warnings. Some browsers blocked access entirely. Mobile clients failed with TLS errors. Our synthetic probes started failing across Europe. US probes were partially successful. That was confusing. Same domain, same endpoint, different results. From inside the cluster, services were reachable. Internal health checks passed. Pods were serving traffic, but external HTTPS requests were failing. We checked the certificate. It looked valid. Correct domain, not expired. Issued recently. So why were clients rejecting it? That contradiction slowed us down. Everything looked correct at a glance. But something deeper was wrong. Initial assumption was certificate expiration, but the dates were well within range. Next thought was DNS. Maybe traffic was hitting an old endpoint. We verified records. Everything pointed correctly to CloudFront. No anomalies. Then we tested manually. I used curl from my laptop. SSL error. Unable to get local issuer certificate. That was more specific. It wasn't saying the certificate was invalid. It was saying it could not verify the chain. We pulled the certificate using OpenSSL. The Leaf certificate was there, but the chain looked incomplete. No intermediate certificate. Now we had a direction. Browsers rely on a full chain of trust. Leaf signed by intermediate. Intermediate signed by root. If the intermediate is missing, some clients fail. But why would it be missing? Cert Manager usually handles that. We checked the Kubernetes secret. It contained the cert and the key, but the full chain bundle was not there. Only the Leaf cert. That should not happen. We checked Cert Manager logs. There was a renewal event about 20 minutes before the incident. No errors. Successful issuance. But something changed after that. We compared the previous certificate secret with the new one. The old one had the full chain. The new one did not. That narrowed it down. The issue started right after renewal. Now Slack was getting tense. Revenue dropping fast. Checkout completely blocked in EU. Should we disable HTTPS enforcement? That was a risky option. Serving HTTP would bypass errors but expose data. Not acceptable. We needed to fix the certificate. Fast. We dug into the Cert Manager configuration. There had been a recent change, a small one. Someone updated the cluster issuer resource. Switching from one ACME endpoint to another. Part of a cleanup effort. At the same time, they modified the certificate spec. Specifically, the field controlling how the certificate chain is stored. They removed the full chain setting. The intention was to simplify the secret. But Cert Manager behavior changed. Instead of storing the full chain bundle, it stored only the Leaf certificate. Previously, NGINX ingress relied on the secret containing the full chain. It did not fetch intermediates dynamically. So when the new certificate was mounted, NGINX served only the Leaf certificate. Clients that had cached intermediates succeeded. Others failed. That explained the regional inconsistency. Some clients had the intermediate cached, others did not. For a portion of users, everything worked. For others, it completely broke. And since the certificate itself was valid and not expired, our basic checks passed. but the chain was broken. We had two options: roll back the certificate to the previous version or fix the chain and redeploy. Rolling back was faster. We restored the previous secret from backup, applied it to the cluster, restarted the ingress controller to reload certificates. Within minutes, handshake failures dropped. Traffic started recovering, but that was temporary. We needed a proper fix. We updated the cert manager configuration, re-enabled full chain storage, triggered a manual renewal, verified the new secret contained the full certificate chain. Then we redeployed ingress. This time, we validated externally, using multiple clients, curl, browser, synthetic probes, all green. We gradually monitored traffic. Error rates normalized. Recovery took about 35 minutes from first alert to full stabilization. What failed was not TLS itself. It was our assumption about how certificates are served. We assumed Cert Manager would always provide a complete chain. We assumed Ingress would handle any missing pieces. Neither was true. Detection was also limited. We alerted on handshake failures, but not on certificate structure, not on missing intermediates. Our validation checks only looked at expiry and domain match. They did not verify the full trust chain. Observability told us something was wrong, but not why clients rejected the certificate. There was also a process gap. A small config change was merged without full end-to-end validation. It passed internal checks, but failed in real client environments. Engineering lessons. Certificate validation must include full chain verification, not just expiry and domain checks. Ingress configurations should not rely on implicit behavior. If a full chain is required, enforce it explicitly. Changes to security infrastructure need real client testing. Synthetic probes should mimic real browser validation, not just basic TLS checks. Backup and restore procedures for certificates are critical. They allowed us to recover quickly. Small configuration changes in security layers can have disproportionate impact. In the end, the certificate was valid, but trust is not just about validity. It is about the chain that proves it.